What if everything we know about the universe is only half the story? We often speak of the Big Bang as the ultimate starting point, 13.8 billion years ago, when time, space, and matter suddenly burst into existence. But what if the Big Bang wasn't the beginning, but rather a transition? Modern cosmology has made astonishing progress in explaining how the universe evolved after the Big Bang. From the formation of galaxies to the mysterious force of dark energy, our telescopes and theories have taken us remarkably far. But there's one question that has haunted scientists for decades. What came before the Big Bang? It's a question that seems almost forbidden, because physics as we know it begins at the Big Bang. Anything before that moment falls into the realm of the unknown, perhaps even the unknowable. This is not just a philosophical curiosity. The answer could redefine our understanding of space, time, and existence itself. Did the universe emerge from nothing? Was there a collapse and rebound, something like a cosmic heartbeat? Or has the cosmos existed forever in cycles of creation and destruction? Until recently, such questions were considered metaphysical, even meaningless. But now, new theoretical models and high-precision observations are reviving one of the boldest ideas in science, that the Big Bang may have been a bounce rather than a birth. And if that's true, we may finally be able to glimpse what came before the beginning. If the universe had a beginning, does it also have an end? That question has inspired two dominant theories for decades, both rooted in how gravity and expansion interact across cosmic time. These theories aren't just intellectual games. They tell us whether the cosmos will fade gently into darkness or collapse in a cataclysmic finale. The first theory is called the Big Freeze. According to this view, the universe will continue expanding forever. But as it does, galaxies will drift farther apart, stars will burn out, and energy will spread thin. Over trillions of years, the cosmos will become dark, cold, and nearly empty, a frozen graveyard where nothing new ever happens. The second is the Big Crunch. Here, the expansion of the universe eventually slows down, reverses, and everything collapses back inward under the force of gravity. Galaxies rush together, temperatures soar, and in the end, the entire universe implodes into a dense, hot singularity, not unlike the state from which it may have begun. Each model implies a radically different fate. One ends in silence and stillness, the other in fire and fury. So which is it? For a long time, astronomers believed the answer depended on how much mass the universe contains. More mass meant stronger gravity, leading to a big crunch. Less mass suggested expansion would go on forever, ending in a big freeze. But then, in the late 1990s, everything changed. Astronomers discovered that the universe wasn't just expanding, it was expanding faster and faster. Something was pushing it apart, overpowering gravity itself. That something came to be known as dark energy, and it would upend everything we thought we knew about the universe's future. In the late 1990s, a discovery sent shockwaves through the world of cosmology. Two independent teams of astronomers studying distant supernovae noticed something strange. The light from these exploding stars was dimmer than expected. This meant they were farther away than they should have been, implying that the universe's expansion was accelerating. This was not supposed to happen. Gravity, the force pulling matter together, should have been slowing the expansion down. Instead, something unseen was overpowering gravity, pushing galaxies apart with increasing speed. To account for this, scientists revived a once-abandoned concept from Einstein, the cosmological constant, a mysterious form of energy inherent to space itself. Today, this phenomenon is broadly known as dark energy. Dark energy is now believed to make up nearly 70% of the entire universe. But what it is, exactly, remains one of the deepest mysteries in physics. Even stranger, recent observations suggest that dark energy might not be constant after all. Data from powerful surveys like the Dark Energy Survey, DES, and the Dark Energy Spectroscopic Instrument, DESI, hint that it could be evolving, changing slightly over cosmic time. If that's true, the fate of the universe becomes far less certain. A changing dark energy could mean that the universe won't expand forever. Instead, its influence might diminish, or even reverse, opening the door to a future cosmic collapse. It's this possibility that inspired theoretical physicist Henry Tye and his team to propose a daring new model. Their idea suggests that the expansion of the universe could one day stop and reverse. Not just a big freeze, not just a big crunch, but something else entirely. If dark energy isn't constant, then perhaps the universe's future isn't fixed either. That's the idea driving a bold new model proposed by theoretical physicist Henry Tye and his team. Their approach combines two powerful, but still hypothetical concepts: axions and a negative cosmological constant. Let's break that down. First, axions are theoretical particles proposed decades ago to solve problems in quantum physics. They're incredibly light, nearly invisible, and interact extremely weakly with normal matter. But what makes them fascinating in cosmology is how they might behave in a young universe. In Tye's model, axions dominate the early expansion of the universe. As the cosmos grows, the energy associated with axions gradually dilutes, becoming less influential. That's where the second piece of the model comes in. Enter the negative cosmological constant. Unlike the positive constant we currently use to explain dark energy, which causes expansion, a negative constant would have the opposite effect, pulling everything inward, encouraging collapse. In this model, axions initially fuel rapid expansion, but over time, as their influence fades, the negative cosmological constant begins to take over. Eventually, it slows down the expansion, and then reverses it entirely. The universe, once flying apart, would begin to fall back in. This elegant mechanism creates a natural cycle: expansion driven by axions, collapse driven by the cosmological constant. It's a recipe for a cyclic universe, one that doesn't begin or end, but instead pulses through endless cosmic rhythms. Of course, this theory relies on some big ifs. We haven't yet confirmed axions exist, and the idea of a negative cosmological constant goes against our current observations. But here's the twist. If future measurements show that dark energy really is changing, and especially if it ever starts to turn negative, then Tye's model could go from fringe theory to frontline science. It might mean the Big Bang was not the first moment, just the latest bounce. If Henry Tye's model is correct, then the universe may not be headed for a frozen death, but for a dramatic collapse. According to the theory, the expansion of the universe will continue for billions of years more. But eventually, as axions lose their influence and the negative cosmological constant grows in dominance, the expansion will slow to a crawl. Then, it will reverse. Galaxies that once raced apart will begin to drift closer. The vast, cold voids between them will shrink. Temperatures will rise as matter compresses. The fabric of space-time itself will begin to tighten, pulling everything inward. This phase marks the beginning of the Big Crunch, a scenario where the entire universe contracts, ultimately collapsing into an unimaginably dense and hot state. Tye's calculations suggest this reversal could begin in about 11 billion years, with the final crunch occurring around 8 billion years later. That means our universe might have a lifespan of roughly 20 billion years from today. But what happens at the very end? That's where things get murky. As the universe collapses into extreme densities, quantum effects, those strange, unpredictable behaviors of particles at microscopic scales, begin to dominate. But our current physics cannot fully describe what happens when quantum mechanics and gravity collide. This is the cosmic blind spot, a place where our equations break down and certainty gives way to speculation. Still, The idea of a collapsing universe opens the door to something extraordinary, because if there's a collapse, might there also be a rebound? What if the universe didn't begin with the Big Bang? What if that explosion wasn't the first, but simply the latest in a long, repeating cycle? That's the idea behind the Big Bounce, a theory that imagines the cosmos not as a one-time event, but as an eternal rhythm of expansion and collapse. In this model, each cycle begins with a Big Bang-like expansion. Over billions of years, the universe grows, stars form, galaxies swirl. Eventually, expansion slows, reverses, and leads to a big crunch. At the moment of maximum compression, perhaps governed by quantum gravity, a new bounce is triggered, starting the process again. This isn't just science fiction. The Big Bounce has roots going back to Einstein himself, who once explored the idea of a cyclic universe. And now, with models like Henry Tye's introducing mechanisms for natural reversal, the theory has gained new momentum. It offers answers to long-standing problems. For example, how do we explain the initial conditions of the Big Bang? Why was everything so hot, dense, and uniform? In a bounce model, those conditions naturally emerge from the previous collapse. It also reframes our place in the cosmos. We might not be witnessing the beginning of everything, but simply the latest act in an infinite cosmic drama. Of course, the Big Bounce remains unproven. We lack direct evidence of previous cycles, and the physics of the bounce itself, where quantum mechanics and gravity meet, is still mysterious. But if dark energy evolves, if axions exist, and if a cosmic collapse is possible, then perhaps the Big Bang wasn't the first, just the latest beat in a breathing universe. We've traveled from the birth of the universe to its possible collapse, and even beyond. But the truth is, we're still standing on the edge of mystery. The Big Bounce offers a compelling narrative. It unites expansion and collapse, past and future, into a grand cosmic rhythm. Yet, so much remains unproven. Axions, dark energy, quantum gravity. In the end, our equations can only go so far. As Henry Tye put it, we might be able to predict how long the universe will last, but not how it will die. Some answers remain beyond the horizon, for now.